Okay, let's look at some problems here. Like the first one, we're going to get you to fill in the gaps. So you've got your notes, so fill in the gaps as we go along. But what we want to do is prove this statement's true. 1 squared plus 2 squared plus 3 squared through to some number n squared would be equal to this statement, 1/6 of n plus 1 to n plus 1. So, and listen, we don't know how many terms we've got, but we'll get this general statement. So what we want to do is, like, if it's true for 1, it's true for 2, it's 3, and so on. It's going to be true for any number. So our proof by induction to prove that this statement is equal to this statement is to say, firstly, let's show it works for some number. So it works 1 for our smallest one is 1. So we put the 1 squared. So because n squared would be 1 squared in this time, and n is 1 in all these states. So 1/6 times 1 times 1 plus 1 is 2. 2 times 1 plus 1 is 3. 1/6 times 1 times 2 times 3 is equal to 1. Okay. It's true for n is equal to 1. So that's a good start. So it does work at some point. We want to prove it works for all. Here's our assumption step. Step 2 is to make that assumption. So really all it is in this case is just replacing n with k. That's all. So, but it's important to realize that statement there, whenever we see it, would be equal to that. So those two are equal. So we're going to use this in our step 3 in our proof. So keep a clear eye on these ones because that we're going to use it. So be really wary to use in our next step. So our next step is to prove that it's true for n is equal to k plus 1. Basically that means we're going to start with our left hand side and prove that it would be equal to our right hand side. So keep in mind that what we're required to prove, now we'll see this a bit. What are we required to prove? We're required to prove our left-hand side would be 1/6 of k plus 1. So if n is equal to k plus 1, and then we would have had we had n plus 1 there, so m plus 1 plus 1, or k plus 1 plus 1 in a bracket, and we put substituting it 2 lots of k plus 1 plus 1. So we're keeping in mind what we're required to prove each time. So we come down with a statement that's going to look like 1/6 k plus 1, and then we're going to have a k plus 2. And this one will work out 2k plus 2 plus 1, it's 2k plus 3. So if we get down to something like that, we've proved that it's equal to the k plus 1 on the right hand side. But we've got to start with our left-hand side. What do we know? We know that this is what we want to solve. But the problem here is this part. Oh, how many missing terms have we got? We could have an infinite number of terms there. But does that matter? Well, it doesn't really when we look at step 2 and see that that part in step 2 was equal to that statement. So what does that allow us to do is to get rid of something where we've got unknown terms into a situation where we've got a complete statement. So that's what we've got. All we've got left over is what? The k plus 1 all squared. And that just keeps added on. So those two statements were equal. That's what we got from step 2. That statement was equal to that statement. So we're able to make that substitution in there and we get the k plus 1 all squared. Now, what we want to do is get from this statement to something that looks like that. So here's where we get our manipulation happening. Again, what do we want to get out? Have a look. We want a 1/6 out. We want a k plus 1. What's common here? K plus 1 is common. We factorize it out. We want our 1/6 out there, so let's get our 1/6 out from that. So the 1/6 will come out from this part. We haven't got a 1/6 there. We've only got a 1 there. So let's get the 1/6 factorized from 1. Gives us 6 there. And so once we've done that factorization, we're left with this statement. We can't factorize anymore, we can't clean it up anymore, except to expand the bracket out and collect our terms, which is not too bad because it comes down to a quadratic. So 2k squared, k, 6k, 6, which cleans up when we collect our like terms to that. Now, again, keep in mind what we're looking to factorize. So we've got the 1/6, we've got the k plus 1 out the front, that's nice. What we want is a k plus 2 and a 2k plus 3. So if we have a look there, is that our factorisation? And it actually happens to be. The 3 times 2 is a 6, 2 times k, so it gives us the 2k squared, 4k plus 3k gives us 7k, and we're done. So therefore, it's true for n is equal to k plus 1. We've proved that when we substitute k plus 1 in to our statement on the left-hand side, we get down to the correct right-hand side that we want. So it's true. And then we make our final statement. Step 4 is the same every time. So, and I keep it so, and I've done it nicely in my notes because I'm able to cut and paste. It works well for me. For you, it's going to be a pain in the butt writing this out all the time. But get over it. So the idea, since the result was true for n is equal 1, from what we did in step 3, it must be true for the next number because it's true for n is equal to k plus 1. So if k is 1, it must be k for 1 plus 1, which is 2. And then, because it's true for 2, it must be true for n is equal to 3. And then you can keep going on for all positive values of n. This keeps going on and on. So there's our induction process. You can see what we mean when we did those first few videos on the algebra manipulation, that it's really important to get that manipulation and understand that algebra, because that's going to be the hardest part. Usually we can do the step 1, step 2 is okay. It's getting through our process of step 3 that's the important part, and this is the critical part of the proof, and where most people fall down, obviously. So really be careful. Again, keep in mind what you need to prove at the end. What are you aiming for? What are you requiring to prove? If you keep that end goal in mind, it sometimes makes it easy to get through those stages of the algebra as we go through the process of the induction.